Okay, so this is our first chapter from Morecroft. So the way I usually like to run these units is we spend a couple of lectures kind of giving material, kind of my spin on it, and then I like to then punctuate, put a bookend on the units with presenting kind of Morecroft's take on the same sort of material so that we can kind of compare and contrast, because modeling is in part a philosophical issue, and so different perspectives are important, and ultimately the perspective that you come up with will be your own spin on things. And so I try to at least have you see sort of maybe different presentations of the same thing. So Morecroft started out with the Monopoly game. I've given kind of several examples here. This, I think, was the on the patent for Monopoly. This is 1935 that's here. But you can see that it's changed in some ways over the years. You can find app versions. You can find versions based on video games. You can find versions based on TV shows. But overall, the basic idea has remained the same. So there's a certain set of salient features that are monopolies. So real estate matters in The Mandalorian as much as it matters in Super Mario Brothers, as much as it matters on an Android or an iPhone, as much as it matters here. And if you look at the monopoly examples from the book, whereas a lot of these names were taken from either New York, places in the West, maybe some fictitious names, but all kind of like sort of US names in the book, it's a London-based monopoly because Morecroft is writing from that group. So the point here is that it's a game, but it captures certain features of realistic real estate here. So it's not something that you could use as a professional real estate agent, but it certainly gets you a lot closer to understanding real estate than you did if you didn't know anything about real estate. And so this is kind of this idea that we have a real world system that we care about. How does real estate work? So we have general ideas about how, what are the important aspects of real estate. We can write them down in simplistic forms. And so we extract the kind of salient features of the environment, put them down, hopefully stripping out the things that maybe aren't as important. So Morecroft's point here is that like this Monopoly game has a jail down here, but it has no police, because the dynamics of the police for this model don't really matter, but it does matter that if you break the rules, you're gonna get stuck in jail. It's much easier to manipulate and study in this form. Not necessarily are you going to learn lessons that will definitely work back in the real world, but at least get you closer so that you can make a more informed action in the real world, test things out here. If they don't work there, then that's great, because that tells you that there must be something that you're missing that's really important. So then you iterate. And so model building is this iterative process of taking what you think is important, trying out only that stuff, seeing how that compares to the real world, and then updating what apparently is important, because if that's all that was important, then it would have matched up better. So we kind of go back and forth there. And so I like this monopoly example that Morecroft leads with. Something else that I think that I like is this idea of monopoly as a game, but we also talk about a metaphor, right? So if a picture's worth 1,000 words, then a metaphor is worth 1,000 pictures. And so cute little cartoon example of this, guy sitting across from a doctor. He has a knife in his back. The doctor says, good news, the test results show it's a metaphor. So there's a metaphor of like, oh, I got stabbed in the back. And if you actually got stabbed in the back, that literally would have a different set of consequences than if you metaphorically got stabbed in the back. But there's something that's sort of, there's a saliency there, which matches. So if somebody double crosses you or does something while you're not looking or when you didn't expect, then they may as well have just stabbed you in the back. And so there's something generalizable about stabbed in the back that goes across contexts that have nothing to do with knives. So metaphors are kind of important. And another metaphor that I will be using throughout the semester is the metaphor of the spectrum. So the definition of a spectrum is a continuous sequence or range. So when we talk about a spectrum, we're talking about something that doesn't have discrete stops. It has maybe two ends, maybe, or at least can be defined by two special points, and everything in between is represented. So a wide spectrum of interest, opposite ends of the political spectrum, implying that there's an idealistic left wing and an idealistic right wing, but in reality, there are people that are all over the spectrum, right? So that's the point there. And I bring this up because this is a powerful metaphor. It's an example of that, but it also can be applied to modeling in general. And so we can think about the spectrum of model fidelity, and we've got our metaphorical models like Monopoly on one end, and then we've got our analog models over here like New York. And I say it's like an analog model because I could run an experiment. I could say, you know, in New York City, this particular strategy always turns out well as a real estate agent. You know, I always can sell things in 72 hours or whatever the metric is when I do this particular thing in New York City. And that is based on experience actually working in New York City. Now, that thing may not apply to LA. LA is a very different type of town than New York City. Chicago, very different. Phoenix, very different. But if we simplify and think about, you know, something like, oh, I don't know, just putting a sign out in front of someone's house, you know, that's something that probably generalizes across these different contexts. But it doesn't get you very far. And, you know, if you want to really optimize your returns, you probably need to actually be closer to the real system. But if you want something that translates across multiple systems, you probably have to be closer to the metaphor. And then there in the middle here, we get what we refer to as illustrative models, which are sort of a nice, they try to be a mix of those. And a lot of these system dynamics models really are meant to kind of fit there. They don't add so much detail, but they have the types of variation that you'd see in a real world system, but they're hopefully more realistic than, you know, a toy model. So because they actually incorporate real dynamics, they have multiple state variables that are interacting in complex ways. So they introduce complexity, but they don't necessarily get all the way to working with the real system. So that's kind of what we're going to be playing with today when we think about this chapter. And I think Morecroft talks about this as, on the metaphorical side, the advantage here is that they're small, cheap, and fast. They're simplistic and generalizable. So even though they leave a lot out, that cost comes with the benefit of being easy to build, easy to run, easy to analyze, and potentially generalizable. On the other side of that, you could say, I'll throw in everything but the kitchen sink, and you're going to get a model that's large, expensive, slow, and very specific. So it may help you really understand the peculiarities of a place, but you're only really going to understand that place. I had a colleague who at one point in his career built this laboratory column where they like sampled a bunch of water from let's say I think it was ocean water, and they built this like really tall column in the laboratory, and it was so it had like a bunch of different fauna and flora within it. Was kind of like sort of this aquarium thing, but it was like super artificial, but also kind of, you know, super specialized to the place that they did all the sampling. And people would joke that it's like you got like the worst of both of these extremes, right? Because it was extremely specific and probably didn't give any lessons about anywhere but there, but it was also so contrived that it probably didn't even model the place that they sampled all the water from. So there's, you know, good and bad ways of constructing these things. We're just talking about scope right now. And so the ideal balance, like say, maximum insight for minimum cost. So when we build models, the tractability and the cost is key. It's not about getting all the details. It's about getting it running so that we can make sense of it. You know, if it takes you a year to build the thing and then you run it and it's just as cryptic as the real system, then you've wasted a year of your life. But if you can spend a week capturing what you think are the important details and get it running, and it turns out that it's a bad match, you've at least learned that those aren't the important details. So even bad models in the middle help you learn about the assumptions you use to build the bad models. So the cost is key. All right, and so, you know, and a kind of another kind of example of that you could build a complex model here. So ultimately, model building is about hypothesis testing. So I give an example here where, let's say I've got, the real Earth over here, a cartoon model of the Earth over here, and I want to say, well, I'm trying to evaluate, temperature change, and what are two hypotheses, that causal hypotheses for understanding temperature change on the planet. And one of those hypotheses could be variations in Earth's orbit. The other one could be the accumulation of a human-produced carbon dioxide. And I could build a model that has both of those in it. I could build a model of the Earth rotating around the sun, wobbling a little bit as it goes, that also has more and more CO2. But that model that has both of those included in it might match what I see outside perfectly, but I have no answer to which one's contributing more. Now, if I instead build simplistic models that only have variations due to Earth's orbit, no change in CO2, or CO2 differences, but no variations in Earth's orbit, and then I ask which one is a closer fit to what we see on the real planet, then that might help me reject one hypothesis, leaving the other hypothesis as a still plausible answer. So one of the advantages of building simplistic models is they allow for scientific control so that we can discriminate among hypotheses. If you throw everything into the most complex model, you might not be able to discriminate among your hypotheses. And that's another reason why you might say it's unrealistic to build a model of the Earth that doesn't have variations, or an unrealistic to build a model of the Earth that doesn't have CO2. And I would say, what question are you asking? If your goal is to discriminate among these two, then this is just a tool for you to create sort of an experimental control. It's a design of your experiment. It's not that you're creating a simplistic model, it's that you're creating an experimental design that helps you tell the difference between these two. So there are uses for simple models. Questions about that? Questions online? Great, okay. So models answer what if questions, keep drilling that down into it. All models are wrong, but some are useful. In other words, details will always be left out or approximated. The question of interest is the model illuminating and useful? In other words, have we included the right details to learn something new? If we've left out important things, or we've put in things that have a real impact on the model but are not impactful in the real world, then it's wrong in the wrong ways. So we know that models are going to be wrong. Our goal is not to make them right. Our goal is to make them wrong in a way that helps us address causal questions generally. Okay. So let's say like Romeo and Juliet, for example. So here's an example of a Shakespeare writes Romeo and Juliet. Maybe there's debate on whether it was originally him or whatever. Not the place for that discussion. Let's assume Shakespeare writes Romeo and Juliet, and somehow it holds on over time. It appeals to contemporaries of Shakespeare. It appeals to people today. They make potentially grotesque, movie adaptations that are modernized with exactly the same script, right? And it still fits. It still feels right. It appeals to people's emotions, and yet it's not a story that anyone ever actually lives themselves. No matter how crazy your teenage love life is, most likely you never came to these extremes where they're battling wars between families, people faking their own deaths, people killing themselves because people fake their own deaths, and so on and so forth. It's an extreme case. It's totally unrealistic. And yet, it's not about faking deaths and anything like that. It's about families and love and things like that. It's not appealing because it's such a weird. It's not Memento or whatever, where it's a weird story. It's appealing because it is so generalizable. So with that in mind, if we view, let's say, Romeo and Juliet as a model of, teenage love, for example, where would we put that model? Would we put it on the left or on the right? So I'm going to just sort of sweep my hand here. And then as I sweep my hand, then raise your hand where you would put Romeo and Juliet. So I'll start here towards analog. No hands so far. I think I'm in the middle. Okay, so hands are starting to go up more and more. And then there's even more there. So definitely a gradient where around here, we start the hands starting to go up there. So yeah, and then online, see if there are any answers to that. Metaphorical, I got online. So yeah, so that's where I would put it too. So metaphorical in that it's goofy, in that if you actually think about it, it doesn't make any sense whatsoever. And yet it makes total sense. And that generalizability, despite how unrealistic it is, makes it a beautiful metaphorical model. On the flip side, well, that's not giving some away, but I can also look, and I think this is another example. Morecroft talks about, not in this chapter, in a later chapter, and I might be mixing in my head, but this is examples of driving simulators. And so if it's hard to see with the lighting here, this is sort of a room with a bunch of individual chairs, each one of them with 3 monitors in front of them. And so there's 5 drivers in simulated cars, and then in front of the room, there's a display that shows the whole track with all of them combined on it. Over here, we see someone, it looks like in their own room with multiple monitors and a similar driving simulator, something similar down here. So here we have a high fidelity simulator where each one of these is a specific car that you are supposedly driving, and possibly immersed with other human drivers driving that car on a relatively recognizable track with grass and things around it. So here, this is a model of driving, a model of probably racing. So where would we put this model? So I'll do the walk from here to there. So I'll start on analog side. Hands I see kind of go up, more hands up. I think I'm in the middle. Hands are kind of going down. And maybe, maybe it's still a couple of hands, but it looked like there was a peak kind of more towards, well, I think there were some here. So it was much kind of a flat distribution, but I'd say most of the mass was over here. And online, between analog and illustrative, analog. So yeah, to me, there is no right answer here. But if I was to compare the two, I would definitely put Romeo and Juliet farther to the right and this farther to the left, just comparing the two of them. This is not like if you were an excellent game player and you put yourself in a real race car, you probably wouldn't win, right? But you might not die. So whereas if you'd never played this game and you put yourself in a race car, you might go straight into a wall. So it's better than nothing. But it also is hyper specialized. If you, if you learned to drive on this, then you put yourself inside a Prius, it's a very different experience. So it's very specialized to a particular model, a particular scenario, driving around these tracks. But it's so it doesn't necessarily generalize to a lot of different cars. But it's probably not all the way learning to drive in the real car. So it's definitely somewhere, maybe over here. So that kind of makes sense to me. So that's good. Now, other sorts of examples. So there are these these are both kind of fisheries examples. So here, this is an example where you can go out into a body of water. You can drop a net that goes down sufficiently far that that the fish that are, so that the region where these fish live is sort of totally captured by that net, and it prevents any introductions or any changes in the population for coming from the outside, but nutrient flow and other aspects of the sort of the trophic patterns there can be maintained. So this you could view as a model of, the inside can be viewed as a model of the outside, for one. And but over here, we have a fisheries model similar to the one we saw in chapter 1, where here you've got fish stock. So this is the number of fish in the fishery. Here's the number of ships at sea, and here's the number of ships at harbor. And so this here doesn't have anything about nutrients, doesn't have anything about predators, it doesn't have anything about sunlight availability, algae, oxygen levels. None of that is in here. So in here, we're really focusing on the health of a fishery subject to the conditions of a particular place. And in order for us to study the population numbers, we need to make sure that the number of fish, there's no introduction of fish or loss of fish to the outside. So that might be all we're trying to do there is just capture, a captive community of fish. But otherwise, everything else, we've got all the details that are right here. So here, anything we learn about this is probably we're going to learn about the health of effectively the outside, and not anywhere else on the planet necessarily. The lessons learned here may not generalize. Whereas over here, if we learn any lessons, the lessons we're going to learn only depend on us having fish, and they have some regeneration properties, which we're going to talk about today. Those regeneration properties are very generic. At some density, you get some regeneration rate. At another density, you get another regeneration rate. The causal factors underneath that regeneration curve are not put into here, but we know the rough shape of them. And so there might be ways to tailor that, but the general pattern we're assuming is kind of held here. So any lessons we learn here are really lessons that could apply to some extent to potentially any fishery. Now, there's going to be some exceptions to the rule, but when there are exceptions to the rule, this will become a lens on why there are exceptions. So if we notice some interesting property that when we go to a real fishery and it doesn't hold up, if it holds up for 99 out of 100 fisheries, for the one fishery it doesn't hold up, we can now go back and say, what's missing? So why do we get this funny result over here? And that will really highlight what's special about this 1 out of 100 fisheries. So the simplicity here is a feature of this model, just so long as we don't pitch it as being the best model of a fishery. So modeling is all about the presentation of the model. If somebody comes to you and says, this will solve every single problem that you'll ever have with any fishery, then that's not an appropriate use of this model. You have to scope the model for the research question and interpret it as such. So sometimes you really do need to go out and build a weird friggin' net. But a lot of times, depending on your research question, this would be way too costly and overkill. And you might not end up learning anything that makes a whole lot of sense. And you might actually learn more from simplifying it and studying it at this very basic level. So I would put this one probably, somewhere over here. I would put this one maybe, somewhere maybe closer to analog, but there's still some kind of weirdness about this, right? Like maybe it really matters that fish can mix, that they're not stuck together inside this shower curtain. So any questions about that? Both of these models can have pros and cons. There's nothing about this spectrum that says that's always bad and that's always good, or vice versa. They're just different. Okay. So for me, if you were to ask me all these models that we've seen so far, this is where I would put them, but there's no right answer. And again, it's more about the relative thing. So, I feel like we can probably agree more on the relative match of these, but even there, this is kind of philosophical at this point. As a modeler, you really care about where your model is and what direction you want to move that model. So you might build this SIR model for epidemic, for disease spread. And as you start realizing that there's some aspect of the disease, like let's say you'd say, well, there's actually this extra set of time where people have the disease, but they're not spreading it yet. And you realize, well, I need another compartment. So they're not just susceptible, infectious, and recovered. Now they're susceptible, exposed, infectious, and recovered. And so at that point, you realize maybe there's something weird about this disease that needs a little bit more realism. So I am going to shift this a little bit toward the analog. And that means I'm going to add more detail. Adding more detail means you're going to have to go out and take out more data to figure out all the other parameters that you've just added. So you will, once you've sort of milked a low order model for as much as it's worth, eventually you might decide to move up. Or likewise, you might start with a really complex model and it doesn't make any sense at all, but you'll come up with a hypothesis and say, wait, it really looks like now that I've looked at this crazy model that this all might be able to be explained by temperature or something like that. So to test that hypothesis, you build a model that only has temperature and see if that's enough to explain the patterns you get. So knowing when to shift one way or another is something that you pick up as a modeler. There's no one right place to live. Now, unfortunately, because of how we educate people, even in higher education, we teach methods and we don't teach, multidisciplinary, thinking. And so, it takes so long to learn one method. And so a lot of people learn this type of model. They learn differential equation modeling, or they learn stochastic simulation, or they learn one of these things. And it takes so long to learn that one thing that they don't really end up getting the breadth to learn enough depth in another thing. And so many careers are built not off of finding the right model, but of finding problems that apply to the particular modeling that you've learned. So, and that's just something that it's just the way we teach. And it's just really a time balancing thing. Like, you don't want to spend more than 4 years in your undergrad. You don't want to spend more than 5 years in a doctoral program. So we're stuck with it. And so hopefully you engage in lifelong learning and you keep learning things so that you're not stuck with just these methods. But a lot of people just stop and you learn how to be really, really good at this type of modeling. So rather than saying, I need to shift this way on the spectrum, you say, I'm going to find a new application that allows me to keep using this type of modeling. And, it's like molecular biologists are probably not going to go out and do ecology. Ecologists are probably not going to do molecular biology. It's rare to find somebody that does both. So they look for problems that goes along with what they know how to do. And that's just how the system works. But in principle, hopefully you collaborate with enough people in your career that if you need to move left or right, you'll have people who can help you move that direction. Okay, so that makes sense. Any questions about that? So here in the class, we are pretty much going to sit closer to metaphorical. We're not quite like, if we were going to build real models that were useful for more than just education, we would want to be kind of more over in this illustrative side. But because we're just starting out with these system dynamics models, we're probably going to have fewer variables than you would need to sort of make really insightful conclusions and so on and so forth. And that's just a function of us, needing somewhere to start. And this ends up being a better use of kind of our time. But once we get comfortable with this, then hopefully coming out of the course, you'll feel like if you had to go and do a term project, a dynamical systems term project in another course or in a job, that you would feel more comfortable that you could take this kind of, simple sort of 5 variable models that we've learned in this class and maybe add a couple of variables and add some complexities. And as we get to things like chaos, which is one of the very last lectures, then we'll start seeing complexities that can come up once you add kind of enough detail. But to start, our models will look probably a little more simplistic than a useful model would normally be. So I'm not trying to say that these models are the best models. I'm trying to say that let's find some place to start. So we're going to trickle in the complexity as we get farther on in the semester. So that fisheries model in chapter 1, probably not the best fisheries model, but it gives you the salient features of all fisheries models, and realistic fisheries models would have those plus a few more details. But once you learn those, that's what all fisheries models will have, and then we'll gradually learn how to add the details as we go and get closer more and more in this direction. So we start here, and hopefully by the end of the semester, can move a little bit closer to the middle. Okay. All right, so spectrum stuff. So before now, we're going to dive into world dynamics next. So all the spectrum stuff sort of makes sense when I talk about analog, metaphorical. Okay, great. Questions online? Looks like we're good. All right, so in the chapter, he brings up Forrester here. So there's unfortunately a lot of history in modeling approaches like this. So we bring up a lot of names that people just associate. And, but there's nothing special about these people that I'm bringing up. They were just the first ones to write about these things. If you talk about system dynamics modeling, somebody's probably going to bring up Jay Forrester, and so, but, if we can not focus so much on whatever this old white guy is, but just generally the general idea, because general idea is not that complicated. So, like Forrester made his nut initially publishing these early. Well, basically, he was a control theorist, and that's another type of modeling that you see in electrical engineering and so on. And he realized that he could take aspects of control theory and simplify them and produce these kind of diagrams that would appeal to people in social sciences and life sciences, and start thinking about kind of bigger problems that were outside of the normal realm of kind of control theory. And this world dynamics was an example of it. And he sort of said that, well, if I go back here, if we think about the world, then really how much of the world's dynamics could be explained by only worrying about basically 5 major things: population, pollution, capital, natural resources, and what he calls capital and agriculture. So we've got these 5 sort of stocks and a couple of parameters. And so you take those things, and then you can start asking, how does population relate to pollution? And so you can start saying, well, if there's more pollution, there's probably more death. And then you can start saying, how do natural resources relate to population? Well, there's more natural resources, there's probably more birth. So you can start drawing all of these connections, and you can take something that looks pretty clean like this, and it turns into this ugly web that looks like this, right? But if you know how to read it, it's not that complex, right? You look for the big squares, like there's population, right there. And you look, these things we'll learn are like valves. So there's birth rate and death rate. And those are like valves of things flowing into the square and flowing out of the square. We're going to learn how to draw all these diagrams. And there aren't that many big squares. Like there's pollution there, there's capital investment there, and then there's this interconnected web. So if I just looked at a little bit of it, I can see population connects to crowding ratio, and then I've got these like conversion rates from crowding ratio to birth rate and crowding ratio to death rate. So I can come up with ways where as the population gets more crowded, there's maybe more death, less birth, and vice versa. And so each individual little connection is pretty easy to explain. There's just a lot of connections, and that's what makes it look crazy like that. But there's, again, just 5 major variables. And so with that, those 5 major variables, depending on how you set up the parameters, you can get, these are the sort of world numbers that have to do with, say, human population. We're just plotting population over time. You can get a simulated trajectory that under certain parameters has a massive, fast peak and then a collapse. And then you can get other sets of parameters that rise more slowly and then kind of settle out at some steady state. And his point was that it's the same fundamental model, just a different collection of, say, how quickly you exploit natural resources, or how quickly the birth rate, you accumulate, more humans, those sorts of things. And so with the exact same diagram, just slightly different values for some of these parameters, you can go from here to there. And so his point was that it doesn't take an asteroid hitting the Earth to get a massive collapse in population. If things are set up right, you can get that for free. It's just a bargain of how the world is set up. It just intrinsically, there's endogenous, the word we'll use a lot, there's endogenous causal reasons for you to get this. It doesn't take an external shock to get these collapses. It all comes from inside. The call is coming from inside the house is kind of what is going on here. But likewise, it's not inevitable. There are other scenarios where the same dynamics can give you steady state. So these properties are not functions of the outside, they're functions of this, I guess I can go back, this web of interconnections. So it's the interconnections that set up the differences between these two. And so when we think about those two, we can start using models like these to try to understand which parameters differentiate between here and there. So in this fisheries example here, so these are real world data. So I've got one fishery. Both fisheries start out roughly the same, but in one fishery in one part of the world, you get a total collapse, and in the other part of the fishery, a recovery. And so the thought is that you could say the collapse might be from some external shock, that just somebody dumped a bunch of acid into the fishery and that was it or something. But if we assume that that's not it, and sort of say, let's just say that what's the intrinsic risk of there being a fishery? Then we can say there's something internal to the fishery that under certain situations would collapse and other situations would recover. And we can use our simplistic model as a lens to say, here are some of the things we think might explain the differences here. If we build an overly simplistic fishery, and yet if we're able to set it up so that some of these parameters lead to these outcomes and other parameters lead to these outcomes, then now we actually have a way to explain a possibility for what's different between these two fisheries. So it's like a microscope where we can zoom in on just these things and see if that's where the explanation is. It might be that for every single way we set this fishery up here, we get only the bottom one or only the top one. And that would mean that we're missing something, but then we can trickle in the things we think we're missing until we get these differences. And then if that then generates that difference, then we can go back to real fisheries and we can start studying that thing. Like maybe it's phosphorus that's the difference here. So if I add phosphorus here and then now suddenly I've got phosphorus parameters that do this or this, I'm going to now go into real fisheries where this has happened and start studying their phosphorus. And I might find that there's key differences there. So the point here is the simplicity here, again, is like a microscope that focuses us on just a small section of possible things that explain the differences here. Does that make sense? That explanation? Okay, so it's not about trickling everything in. It's about strategic models that set up multiple scenarios with different parameters. One model, different outcomes. That means that one model can help us figure out what the difference between the outcomes are. All right, now, this chapter is really about system dynamics modeling in general, but it might be read as an endorsement to Forrester's limits to growth type, so a lot of this limits to growth stuff that Forger came up with, when people read this largely turned into things like peak oil. And so people thought, well, that there would be, based on these types of models, there was only one outcome, that we'd eventually hit, exhaust all our resources and we would end up in this collapse here. And I'm not sure that that's exactly what Forrester was trying to communicate, but the economists came into play and they said, you know what, you're missing a lot in your model here. And so if you take SOS 325, it's another course that I've taught before. When I teach it, we use this book, and I think some other faculty use this book. They have a whole section on Forrester and limits to growth. And they point out that, that Forrester made a lot of assumptions in these models that probably don't match human behavior. So they were too restrictive. So I think I highlight a couple of things that they specifically say here. So, so I'm not going to focus, but the biggest point that they make here is that there are dynamic feedbacks that are not being modeled here that happen when resources become scarce. So if you get a scarce amount of oil, the price of oil goes up. If you get a scarce amount of any resource, the price of that resource goes up. And over time and time again, we've shifted from one energy source to another, largely due to the economics of the extraction of that resource. Now, that doesn't mean that's not going to save us. Like if the population keeps growing and keeps growing and keeps growing, I mean, you can only consume so much. But the point is, if you just focus on one natural resource, then you're probably missing a lot of dynamic feedbacks that are really important in the real thing here. So economists have sort of an economic optimism where as long as you can control access to natural resources, then you can sort of price dynamics will actually adjust consumption patterns to damp some of these things down so that we'd be more likely to be in this scenario than this scenario. And so they criticized Forrester for not allowing for price dynamics to be in here. But the thing about that, and that's what is that we can add price dynamics to Forrester's model. And in fact, we're going to learn about the global oil market, a model for it in chapter 8 after the midterm. And there we actually do add price dynamics in based on oil availability and so on. And we get very interesting dynamics that come out from having changing prices. So The criticisms the economists have about Forrester's limits to growth are not criticisms about system dynamics modeling, because economists do dynamical systems modeling. So we can criticize Forrester's model while not having to criticize the modeling approach in general. So these two things can really live together, is what I'm kind of saying here. So I don't want the chapter to seem like an endorsement of Forrester's model, but I also don't want you to think the economists are totally saying that you shouldn't be using system dynamics modeling. There is a happy in between where you can add dynamical responses to economic models to have kind of make everybody sort of happy. And that's exactly what economists do when we think about natural resource stuff. They often focus more on static models, but they when they really get the hyper realistic modeling, then they actually add the dynamics in and use the exact same framework. So that's the difference between Forrester and system dynamics modeling. And we'll see again more of that down in like chapter 8. But if you're really interested in this kind of debate and all of the stuff about it, again, SOS 325, it's a really nice complement to this course. 325, very different way to model things. It's not computational, it's economic. So it's a way of thinking about natural resources with kind of an economic perspective, thinking about human behavior and so on. And so that's, putting those two things together helps you build some pretty interesting models. All right, so any questions about that? Find my mouse. Okay, so Forrester sets up in this chapter some these stock and flow models. We haven't learned how to build these yet, so you were not supposed to. How many people have seen stock and flow models before? Okay, so quite a few of you. So this is at least these diagrams shouldn't be too foreign. But for those of you who haven't, it's no problem. This is exactly what we're going to be learning before the midterm: how to read these things, how to build these things, and how to simulate these things. But so Forrester is somewhat foreshadowing what we're going to be doing in the next couple of lectures. So this is kind of thinking about what's going to come out of that. But the basic idea here is that these are models in which are captured by so-called stocks. So these, you can think of a stock as sometimes they're called assets or resources. These are things that change over time. So they have a state. So sometimes we also call them state variables. So they have a particular state. So this orange, you can think of this as like orange liquid, like Tang in a bucket or something like that. And as you fill it up, this line would go up. As it is depleted, the line goes down. So you can imagine this being a bucket that the current height of the bucket is the state of the variable, and that changes over time. And there's flows going in. So if you turn the inflow up, the level rises. If you turn the outflow up, the level falls. And so we will build mathematical expressions that will set up inflows based on the levels of these stocks and other stocks in the system. And that's what creates these dynamic patterns over time. So the stock is the thing that changes over time. The flows are what make it change over time. And the flows are a function of all the stocks. So with these stock and flow models, so there was this optional. So he's got some models that has already built, and they're runnable with this software called iThink. And if you on Canvas, I've got under the course information page, there's a link to how to download iThink if you want to use and try out the models that he's built that are distributed along with the book. You don't have to, though. And all the chapters that we read, just looking at the screenshots in the book will be enough to kind of capture the main points. But if you want to experiment with it, you can follow the instructions for getting iThink and running his models. And one of these was this fish stock demo, and I think I've got a video of this here. So this is me running iThink, got this fish stock video. You can see the mouse kind of moving around, and it's got, and let me probably just prepare myself to pause if I needed to here. So basically you can draw the fish stock in here. You can have readouts. So this is saying that there's currently 1,900 fish in the stock. It's saying that there's a constant rate of 200 fish per year. There's a constant catch of 200 fish per year. And this is the current time at year 0. So they're going to run for 40 years in intervals of 10. So every 10 years it stops, and then it changes these rates, let's say due to some exogenous, some outside of the model factor. So they're, I think, going to change the catch rate. So they're going to say, let's say that in year 2, they catch more fish. In year 3, they catch less fish. What happens to the fish stock? So if we go ahead and try that out, if I can get the mouse back. So so if you hit play on these things, then it's got an interface where you can see after 10 years, notice that there's no change in the fish stock. So, so here we can see that for the first 10 years, so this, we should probably learn how to read these diagrams because they're going to use them all throughout the rest of the book. So up at the top here, there's a little line that says 1 fish stock right here. It says 2 new fish per year. It's in red right here. The fish stock is in blue, so blue, red. And then over here in green, it says catch or harvest rate, and it says a 3 down here. So then on which one of these lines, they're color-coded and numbered. So the blue one's got a 1 on it, and it's going to start going down. This red one's got a 2 on it, and this green one in this little corner's got a 3 on it. Now, if you look on, this is the tricky thing. But if you look on the axis here, there are 2 numbers, 4,000 and 400, down here 2,200, and down here 0 and 0, corresponding to these major axis ticks. Those 2 numbers represent different axes for different lines here. So it's really subtle, but if you look far over on the left here, and it's really hard to see probably in class, but if you look at this one next time you're looking at your book, it has 1, 2, and 3 written vertically. And in that 1, 2, and 3 there, the 2 and the 3 have a little bar showing that they're together. It says 2 and 3 are kind of connected together. The way we read that is the top number goes to line 1, and the second number, 400, goes to both lines 2 and 3. So this is a way of them saying we have 3 lines and effectively 3 axes, but 2 of the axes are the same, so they just compress them into one axis number. So that's why this tick has 2 lines. The 4,000 corresponds to the blue line, and the 400 corresponds to both the green and the red. All right, so any questions about that? So you're gonna see this plot, and I might use some of his plots on midterms and things like that, so we should get used to reading it. The advantage of this is it's very readable in black and white, but disadvantage is it's maybe a little bit new to read these things. But that makes sense. It says 1, 2, and 3. The 2 and 3 have a line next to them, so those correspond to the bottom. The 1 doesn't have any line, that corresponds to the top. So the number of axes, the number of major tick labels will correspond to the number of groupings over here. Okay, so for the first 10 years, the inflow and the outflow, the new fish per year and the catch or harvest rate are both held steady at 200. So there's 200 new fish coming in and there's 200 old fish going out. So the system's perfectly in balance. And that's the reason why the blue line is holding at 1900. And so that's this 1 here. Then at year 10, the red line, new fish per year, stays constant at 200. But then they decide it's not part of the dynamics, just they ramp up inside the model as if there is an outside force, ramps up the catch rate from 200 up to 300. And while it's ramping up, there's now a gap between the catch rate and the regeneration rate. And that's going to cause the fish stock to fall because the outflow is greater than the inflow. So that bucket is going to get lower and lower and lower. And that keeps happening until the next 10 years. And then we bring the catch rate back down to 0. So you see the rate level off as they come, these are matched up again, and then it gets constant again. So if I were to run that back in the interface here, then it's just another visualization. The first 10 years, the inflow and outflow are both 200, the fish stock stays constant. The next years, the outflow gets bigger, and so the fish stock declines. In the next year, the outflow gets closer and closer to the inflow. And then in the last group, these are balanced again, so that stays constant. So that's how we look at these stock and flow diagrams over time. So any questions about those visualizations? Okay, questions online? All right. All right, so let's look at the stock and flow diagram here. So this is a really simple fishery. In this simple model, we don't even have the harvesting. This is just the fish by themselves. And we got the fish stock here. We say this diagram is saying that the number of fish in the fishery determines the fish density. So the maximum fishery size here, if you take the number of fish divided by the maximum fishery size, you get the density. We have some net regeneration curve that we're assuming has been given to us by population biologists who know the relationship between density and regeneration rate. And given that regeneration curve, we put that into the inflow of new fish, and that ends up changing the fish stock. So there's a feedback here where the number of fish in the fishery determines the regeneration rate, which determines how many new fish and thus how the fish stock changes over time. So there's a feedback that's encoded inside this diagram. And if we look at that feedback, the really important how we characterize the feedback depends on the density. In other words, it depends on this net regeneration curve. So inside this net regeneration curve, there is a diagram which maps fish density on the x-axis to net regeneration on the y-axis. We're going to end up calling these lookup tables later in the semester, because instead of writing a formula for them, we just capture it with a graph where you kind of put an input in and you look up what the output's going to be. So we're going to call this a lookup table. And in this lookup table, for all densities lower than this kind of intermediate density, there's an upward slope. And that upward slope means that for low densities, then at a low density, you're going to get a positive regeneration rate, which is going to lead to more fish, which is going to increase the density. So when this curve, this net regeneration curve, has this slope, we refer to this as a reinforcing feedback loop or a positive feedback loop, because fish get more fish, beget more fish, beget more fish, all the way to this point up here. Now at high densities, the story changes. At high densities, then you start getting, this is a model of intra-specific competition. So the idea here is at low densities, if there's two fish in the fishery and they never can find each other, it's going to be hard for them to reproduce. But if you go from 2 fish to 200 fish, it's going to be pretty easy for the fish to find a mate. If you go to 300 fish, it's even easier for them to find a mate, just so long as there's enough food to produce enough offspring. You go to this point here, now you got intraspecific competition. Now, even though they can find a mate, that offspring can't survive because they can't find enough food to support the 3 of them. So as this side of it, as you go from one density, you still have a positive regeneration rate, so the fishery is still growing, but it grows less and less fast as you get a higher and higher density, because you get a higher and higher density, then those food restrictions start kicking in. And so that's what we see here in the density regeneration rate relationship. How that plays out over time is that when you start the fishery with a very few number of fish in it, then they're at low density, so they have a high regeneration rate. So I've got 2 things plotted, fish stock and new fish per year. So fish stock is line 1, new fish per year is the kind of peak here. And so at low densities, we get more and more fish per year and it ramps up. So we get an acceleration in the fish stock, but then it hits that critical density up at the top here. And after that critical density, then the regeneration rate starts to decline, even though the number of fish is increasing. And when the regeneration rate hits 0, then we hit what's known as carrying capacity. And that sets up S-shaped growth. So this is logistic growth or a sigmoidal growth in a fish population, all captured by this curve right here. Okay, so are there questions about this basic idea? I think I've got model of mate availability. And for those of you who are in conservation biology, you might learn about an Ali effect eventually, which is sort of a relationship between density and fitness. And if you look at this, because there's kind of an extra kink here, that extra kink is modeling what's known as an Ali effect, which is kind of outside of the scope of this class, but I just put that in there if you're wondering why is there like a weird kink here, but and then it otherwise looks pretty symmetric, and that's what they're getting at, is they're adding that extra complexity. So does that basic idea make sense? And this is something that we'll revisit in clearer forms as we go on. But in this compact model, upward slope is positive feedback, downward slope is negative feedback. So the curve, like in the model, it all looks like one loop, but whether it's a positive feedback loop or negative loop depends on the density. Okay. All right, so that was the main fishery model there. And what we're going to see throughout the semester is that whenever we have a reinforcing loop sort of next to a balancing loop, we tend to always get S-shaped growth. So although we're studying this in a specific example of a fishery, what we end up finding is that there's something that generalizes to any system that has a reinforcing loop at low levels of the system and a balancing loop at high levels of the system, is that you get S-shaped growth. And so what we're going to build throughout the rest of the semester, and this is similar to what you'd see in sort of systems thinking, is different dynamic hypotheses, where once you look at a diagram, before you even run the diagram, you'll be able to guess at what the modes of the system are. So you'll be able to say, this is likely to have S-shaped growth. This is likely to have oscillations, and so on and so forth. And that will actually help you, because if you want to explain things like oscillations in real data, you'll know sort of a design pattern to start with. Like, well, I know that generally oscillations look like this pattern, so I'm going to start with this pattern and see if I can figure out what the variables are in this pattern, and then I can embellish as I need. But that's what this sort of fishery is like. Even though we say we're learning about fisheries, we're generally learning about any system that has a reinforcing followed by a balancing loop. So that's kind of where we're going with that, is these dynamic hypotheses, which we'll introduce here in chapter 5. And we'll also talk a little about it in one of the upcoming readings. So he's got a demo of this that you can run with I think. And then you can add on, and that's what he does in the chapter, we just took that fishery that we just talked about here, and then we just added another link to harvest rate, where we have this catch now, which is new, which depends on the number of ships at sea. So we have the same fish population dynamics, but now the outflow, which used to be set just by the death rate of the fish, is now going to be set also by the number of ships in the fishery. And so this allows us to have a way to play with kind of this new predator-prey system, where we've got ships as the predators and fish as the prey. And to make that connection, there's this special variable that they talk about in the chapter called effective fish density of catch per ship. And early in the chapter, they say, well, what if it looks like this? And late in the chapter, they say, what if it looks like this? Now, biologists, when you look at these two curves, have names for these two. Well, for one, this thing is called a functional response. And so when you have a predator-prey system, you need to know how does the intake rate per predator vary with the density of the prey. And that relationship is fundamental. It generalizes across all predator-prey systems, that it tends to be really important. And that's what we call the functional response. And it turns out that in models of predator-prey systems, the shape of the functional response totally changes qualitatively the outcomes that we get in that system. And although Morecroft doesn't call them this, this is where he came up with this whole chapter, is that this is like population bio 101, is that you need, or sort of ecology 101, is that we start with a so-called type 1. Usually, if I was to teach a theoretical biology course, we usually start with this one, and then we go to this one. But he kind of flipped it on you, and he created this funny cunning fish. But we're going to find out that the fish don't have to be cunning for this to make sense. But he just sort of was hand waving and saying, like, here's a way in which you could get this sort of response here. So in the chapter, sort of functioning on this, so a type 2 response, what we mean by that is at high densities, the predator's speed sort of is what sets the catch rate. So it's like, it's not even though the fish density increases, because it takes so long to move from place to place and to haul up a catch of fish, that amount of time it takes to haul up that catch of fish prevents you from really realizing the benefits you get from the increased density. And that's what creates a type 2 functional response. The handling time of the prey becomes so long that it doesn't matter if the prey are more dense. And the interesting side effect of this for fisheries is that psychologically, this means that from about 60% density to 100% density, the density feedbacks are not going to be felt by anyone out there, because you get the same catch rate at the boats, regardless if you're 60% density or 100% density. So if you try to come out to them and say, hey, you guys got to stop fishing so much, the density is really decreasing, they're going to say, well, you're crazy. We get the exact same catch this month as we did last month, as we did the month before that. They don't realize that they've been crawling this way, and their catch might have only been moving this much, but the density in the fishery has been using gigantically. So that's a psychological effect of that. That psychological effect is not in the model. It's just a practical side effect of this type of response. All right, and then a type 1 response is actually the simpler response. This is like the overly simplistic idea of how you might expect predator-prey relationships to work, whereas density increases, catch rate will increase. But in reality, when you do experiments, and so there's a person named Holling who first kind of came up with this, and they would put humans, and they put a bunch of sandpaper discs, and you'd ask the humans to touch as many discs as possible. And if there are low densities of discs, then as you increase the density of disc, then the rate at which they touch the paper discs went up like this. But once you got to a critical density, the time it took for them to move their hand around slowed them down so much that it really didn't matter if there was 60% density or 100% density, they had the same touch rate. And so that was from an experimental model, which then they fit to these models. So now when you build this system, this is a critical parameter. What type of functional response do you want? And it has to do with the handling time. All right, so that's what was going on here. So here you've got continuous feedback between the two variables. Here, feedback's broken where it's flat, and continuous where it's low. So that's what I mean by type 2 functional response. And that's all I'm sort of explaining here. All right, so any questions about this idea of this type 2 functional response, the non-cunning fish? This is kind of the more realistic predator-prey situation. Okay. So when he did this, then he generated these outputs where the fishery collapsed. And I don't want to go into a whole lot of detail here, but the big thing that I want to point out is that when we're reading these diagrams, we need to figure out, how do we quantify sustainability? And I know that this is not a sustainable situation because the fish stock goes to 0, so that's not good. So you could claim that, well, the catch rate and the new fish per year come into balance, but they come into balance at 0. So that's also not sustainable. So when I look at this, I see a bunch of, a spaghetti mess of lines or whatever, but the key thing we take out here first, not sustainable. The other thing that's interesting here is that we had plenty of fish when the number, so this orange line is ships at sea. When there were this many ships at sea here, right here, I had plenty of fish. When they raised the ships up to this point, the fish plummeted to the point where when they decreased the fish back to what previously seemed to be fine, it was too late. So we're going to learn in later chapters about something called a tipping point that they've gone over in this dynamical system, where even if you bring the ships back to a previously okay level, the system is tipped over and it can't recover. And so we'll learn how to find those later on. But I want to get, before we end here, to this cunning fish thing. So they said, well, what if the fish knew how to kind of avoid the ships, so that when they're at high densities or at low densities, they had kind of the same probability of being caught because the fish were somehow cunning, like smart fish. And so, so you get this sort of the same response across all densities. And the interesting thing is when you have this, what ends up happening is that as the fish density, or as the number of fish decreases, the catch rate, which is this 3 line, also bows out. So you actually see a decline in catch that we didn't see in the old model. And that decline in catch allows the system to actually come into balance. And so you can see here that this catch rate, the green line, and the new fish per year, the red line, they end up coming in to balance here, and we get a sustainable outcome. So how do we quantify sustainability in a graph like this? The inflows and outflows match, they're balanced. That's the one way to view it. The other thing is the critical stock that we're monitoring here comes out and stabilizes at a non-zero value. So this is a picture of what we'd expect a sustainable outcome, a textbook sustainable outcome to look like. So that's kind of what we were trying to communicate here. So does this make sense? Why this is, if I could show you these two graphs and ask which one depicts a textbook toy model of a sustainable outcome. And I hope you could pick this one because the fish stock is non-zero and the inflows and outflows are balanced. There's not, you don't get a constant persistent outflow greater than inflow. Does that make sense? Are there any questions about that? Okay, great. So this cunning fish, this linear relationship, reduces the fall in fish stock by reducing catch, allows them to come into balance. And the additional thing that is not in the model, but would be a side effect of the cunning fish, is that the people who are fishing, the professionals out there who are fishing, actually will notice when the density decreases because their catch will decrease. Now, the thing is, you could say, well, what the heck are cunning fish? There's no allele for a cunning fish that is going to spread through the population and save the day. But if we know that a type 1 functional response is going to bring us into balance, then what we might be able to do, as an example, is try to emulate a type 1 functional response through regulation. So let's say I am a regulator who sells quotas for operating in the fishery. If I have a way to estimate the density of fish in the fishery, I can then, on the quotas, give people different quotas based on the density that is in the fishery. So at low densities, I give them very low quotas. At high densities, I give them very high quotas. Now, even though the people out on the fishery can't detect changes in density, they can feel changes in density through the regulation. Now that's assuming that that my regulatory agency is smart enough to be able to estimate the number of fish in the fishery, which, let me tell you, is not easy to do. And B, that the people I sell the quotas to, sell the licenses to, actually abide by the quota. Now, so those are big assumptions. So what we're going to see in a later model in the book is a model of exactly what I'm talking about here, where we're going to have to model the uncertainty in the estimate of the density, and we're going to have to model the compliance rate of the industry professionals, and we'll have to see under what compliance rates do we actually get sustainability. So if we assume, let's say, an 80% compliance rate, what are we going to have to set our quotas to? So that's kind of going to be the interesting thing, is that if people abide by the rules, they actually could fish more. But if we count on people not abiding by the rules, we're actually going to have to set lower quotas because we need the safety margin to deal with people not actually abiding by the quota. So there's some interesting things that go into there. So we can keep adding on the complexity as needed, but I think it's really illustrative to start with the simple models, to sort of say these are our aspirational goals, to really understand the salient features of a sustainable outcome, and then try to build policies that achieve the sustainable outcome and then deal with the contingencies for the problems with those policies. So we build those up, we kind of stack the onion up as we go. All right, so questions. It's kind of, those are the key things that I wanted you to take from this chapter. But I know that a lot of the modeling frameworks are still new this chapter is an intro for the rest of the book for the rest of the semester. We're going to start next lecture at causal loop diagrams, so we're like way back at the beginning. All right, so with that, so as you're packing up, just have the announcements, and I do have the attendance question. Only thing I'll mention, Muddiest Point due on Sunday. Don't forget about that assignment, where the mental model assignment, I think a large portion of the class has already turned that assignment in from last week. That's due Sunday as well. And then I think VinSim is now on these computers, but if you want to bring your own computers with VinSim installed on, that's fine. Otherwise, you can also use Insight Maker on the web pages. And then there's a reading coming up for lecture B3, but that's not next week, it's the week after that. But you might start thinking about that. All right, so attendance exercise, just to give you credit for being here, then I'll try to put the question also in the chat. The question I'll have here is, what type of functional response were the cunning fish? Was it a type 1 or a type 2? And remember, these are not graded for correctness, they're graded for coherence. So as long as you do 1 or 2, you're going to be fine. But is it a type 1? Is cunning fish a type 1, or is cunning fish a type 2 functional response? So I'll put that here. And that's all I got for you. So have a good weekend, and we'll see you Tuesday.
Are you posting these slides or just the lecture?
The slides are posted.
Where are they posted?
If you go to the lecture pages and click on one of the lectures, the slides should be inside that. Yeah, the PDF version of slides, at least. If you have trouble, just send me an email, and I can look you up. Any other questions online? If not,
I got like a little bit confused, but like it makes more sense now looking at the cunning fish.
okay, good.
Graph format, but it was talking about how with the cunning fish, the process became linear.
Right.
Is that what that's? It was
that's
talking
right.
about a graphical representation.
That's what it's with the density versus catch rate. Right. That line, that's what they mean by linear.
Yeah. Okay. Because when I was like trying to picture the like the model,
right,
essentially,
right.
And then I was like, well, wouldn't that be like, you know, it would make it sustainable, like we saw. So like it wouldn't be linear because it would be like,
oh, like it would be regulated or something like that.
Yeah. So I was thinking of it in that terms.
Oh, it's a very nonlinear and linear overloaded terms. They're going to be used in lots of different contexts. So yeah, I get that. And whenever something like that comes up, just let me know. Other people are going to have the same question. So that linear was just that relationship.
Oh yeah,
but,
as soon as I saw that graph, boom.
Yeah.
Okay.
Good.
Yeah, so I just wanted to make sure.
Yeah. Thanks.